Hey everybody, I'm not going to say that this is number theory lecture 13. I'm going to make this a continuation of number theory lecture 12, where we do no theory, just problem solving with Diophantine equations. So we're going to work out a few exercises here. Diophantine equations in two variables, maybe three. We'll see. Let's look at this example. The neighborhood theater charges $1.80 for adult admissions, 75 cents for children. On one particular evening, the total receipts were $90. Assuming that more adults than children were present, how many people attended? My goodness. Total receipts were $90. $1.80 for adults, 75 cents for. My goodness, how old is the book that I got this problem from anyway? I'm just venturing a guess that book may be at least as old as I am. Oh, I shouldn't do this, but I'm going to. In 1994 or 1995, almost 30 years ago, I was in Williamsburg, Virginia. I was at a week-long math conference at William and Mary, and at night I was staying in a dormitory. There was nothing in the dormitory except a bed. So on Friday night, since I was staying over the weekend, I thought, I don't want to stare at the four walls. Monday through Thursday, I went to the computer lab at night and worked on the exercises that we had been given to do at this conference. But the conference was over Friday afternoon, and Friday night I didn't want to stare at bare walls for 6 hours and then go to sleep. So I left on foot to go to a movie theater, and it was a few miles away. But I got there eventually, and I was there to see Apollo 13. That's what I was there for. And while I was standing in line, and there was quite a long line, I struck up a conversation with the woman behind me. And when I finally got to the head of the line, the person that was selling tickets said, "That'll be $10, sir." $10? That? Oh no. She and I are not together. We're just talking. And he said, "Yes, I know, sir. That will be $10. Okay. Well, that was shocking to me anyway for 1994 or 1995. Today it probably wouldn't be. But anyway, total receipts are $90, $1.80 for adults, 75 cents for children. More adults than children present. So how many people attended? That's our exercise. Sorry for pausing so soon in the lecture. I hadn't really thought about how I was going to do this exercise, and right before I paused, I thought, wait a minute. The thing to do is to let A be the number of adults and C be the number of children, A and C, and then I thought, no, I don't think I really want to do that in this case, because in our model of the Diophantine equation with two variables, A is one of the coefficients, and C is the total number of whatever we have on the other side of the equation. And so I thought, you know what? Instead of using A and C, which are part of our model, I'm going to let, oh my goodness. Oh, well, this is perfect. Yep. I'll let X be the number of adults and Y be the number of children. Now, this is a Diophantine equation, so we're dealing with integers, whole numbers. That's not a whole number. That's not a whole number. At least if we're looking in terms of dollars, these are not whole numbers. So you know what I'm going to do? I'm not going to do this equation in terms of dollars. I'm going to write this equation in terms of cents, okay? So admissions for an adult, 180 cents. So this is the amount of cents that's taken in per adult. And the admission for children is 75 cents. And the total receipts are not $90, but 9,000 cents. Okay, that's the equation that I'm going to work with. And just as a reminder, X, the number of adults, is greater than Y. We're not going to use this fact right away, but at the tail end of this exercise, we will use this fact. So I just wanted to write this down at the get-go so that we'll keep it in mind. Okay? Let's start. Okay, what do we do first? First thing we do is decide whether the equation actually has a solution. And this equation does have a solution exactly when the greatest common divisor of A and B divides C. And the greatest common divisor of A and B is greatest common divisor of 180 and 75. Holy moly. Well, I'll hit the chicken switch. Let's see. 180, that's 2 squared times 45. And 45 is 5 times 9. So this breaks down to 2 squared, 3 squared times 5. And 75, that's a little bit easier. That's 3 times 25, which in terms of primes is 3 times 5 squared. So both 180 and 75 have at least one factor of 5, one factor of 3. 75 has exactly one factor of 3. And both 180 and 75 have at least one factor of 5. 180 has exactly one factor of 5. So the greatest common denominator is just the product of the primes that they have in common. That's going to be one factor of 3, one factor of 5. So D is 15. Okay. Let me see now. Does D divide C? And again, D is 15. Does 15 divide 9,000? Oh, I'm pretty sure it does. There's a 3 in both of these. There's a 5 in both of these. Let's see, 9,000 equals 15. What is it, 600? I think so. D does divide C. And that means solutions do exist. So if we proceed, we will not be wasting our time trying to find a solution that doesn't exist. Okay, onward and upward to step 2. What is that? Find a particular solution. A particular solution of this equation. You're absolutely right. Okay. Here we have to find a particular solution to the related Diophantine equation. We don't know how to find a particular solution to this directly, so we swallow our pride and we take an intermediate step. AX plus BY equals D, where D is the greatest common divisor of A and B. Okay, let's get to it. How do we find the greatest common divisor? I'm sorry. How do we get X naught and Y naught to make this true? Do you remember? We apply the Euclidean algorithm to 180 and 75. The larger of the two is the dividend. The lesser of the two is the divisor. And so we have dividend equals some quotient times the divisor, which is the smaller of A and B, plus some remainder. Oh, thank goodness, this is easy. 2 times 75 is 150, and that will leave us with a remainder of 30. Oh my goodness, the arithmetic's so easy, even I can do it. This is great. Now what happens? The old divisor becomes the new dividend. And the old remainder becomes the new divisor. Oh, this is great. This is, I can do 30 into 75. 75 is 2 times 30 plus a remainder of 15. Oh, this is wonderful. And one more time. The old divisor becomes the new dividend. And the old remainder becomes the new divisor. Oh my goodness, that was so easy, even I could do it. The last non-zero remainder is the greatest common divisor. Looks good. Now we're going to reverse engineer these equations to write the greatest common divisor in terms of preceding dividends and divisors. So let's see. I will call this equation 1. I'll call this equation 2 for future reference. Okay. From equation 1, we take the greatest common divisor, 15, and write it in terms of preceding dividends and divisors. So 15 is equal to 75 minus 2 times 30. now we work our way backward. We take the lesser of the two and write it in terms of preceding dividends and divisors. From equation 2, 30 is equal to 180 minus 2 times 75. And you know what? I'll give this equation a name. I'll call this equation 3. Because this equation gives us the greatest common divisor in terms of preceding dividends and divisors. And I'm going to take this and plug it into equation 3 in place of 30. So that'll give me 15 is equal to 75 minus, 75 minus 2 times 30. But 30 is equal to this mess, 180 minus 2 times 75. And I will just simplify that. 15 is equal to, let's see, I have negative 2 times 180 and I have negative 2 times negative 2 is positive 4 times 75. So this is 4 times 75 plus another 75 is 5 times 75. Okay, that looks good. Now, one of these equations, for the sake of board space, I erased part of it. And let's see, what was it? 180 plus 180x plus 75y equals 15. Okay. And I wanted to make sure we see this because our next step is rewrite in the exact form of this equation, 180x plus 75. Rewrite in the exact form 180x plus 75y equals 15. Do I have enough space? By golly, I think I do. Okay. So this equation becomes 180 times negative 2 plus 75 times 5 equals 15. Yep, by golly, we squeezed that in. find a particular solution to this equation. 180 times negative 2 plus 75 times 5 equals 15. Here's our x of naught. Here's our y sub naught. Okay. We did part A. Now, what's part B going to be? As far as finding a particular solution. Well, let's see. The only difference between this equation and the one that we started out with is that this is not equal to what, 9,000? So I guess we just multiply both sides by whatever we have to multiply by so that this becomes 9,000, right? Well, we'll just check it against our list of steps. By the way, our next step is to multiply both sides by whatever we have to multiply by to make this thing equal to 9,000, which is our C. We've already done a step that I didn't note. Which is we take this result expressing the greatest common divisor in terms of previous dividends and divisors. We rewrite that in the form of ax naught plus by naught equals C, equals D rather. Yeah. So that was our second step. Ax naught plus by naught equals D. And we remember this particular solution to the related Diophantine equation. Now we're on to step 3, or step C rather, where we multiply both sides of this equation by whatever we have to multiply it by to make this thing equal to 9,000. And that magic number, since this is D, and we want this to become C, that magic number is just going to be C divided by D. Multiply both sides of the equation by C over D. Holy moly, let's see. C is 9,000. D is 15. 15 goes into 96 times 6,600. Okay. I think that's right. I multiply both sides by C over D, and I'm going to do this in a special way. Notice that I just wrote 600 times the entire left side. I have to distribute 600 to each of these terms, and here's what I'm going to do. Since I don't want A to change and I don't want B to change, I'm going to distribute the 600 to the numbers inside the parentheses here, so that I'll still end up having 180 times something. and 75 times something. And those somethings are going to be the x and y coordinates, if you will, of our particular solution. $180 times negative 1200 plus 75, let's see, 600 times 5, 300. I don't like that at all. Let's see, 5 times 600 is less than 600. I don't believe that for 1 minute. I may be stupid, but I'm not that stupid. Okay. 600 times negative 2, negative 1200. 600 times 5, 3000. Okay. I think I just rediscovered my brain. Equals 600 times 15, that's 9,000. And what have we here? X of p, the x coordinate of the particular solution of the original Diophantine equation, and y sub p, voila, we got our particular solution. The rest of this exercise is going to be pretty easy. We just did steps A, B, and C of step 2, which is find a particular solution to the original Diophantine equation. Step 3, what is that going to be now? We have a particular solution, so what is there left for us to find? Find the homogeneous solution? Absolutely right. Find the solution to the related homogeneous equation ax plus by equals 0. Okay. Here's our A, here's our B. And what is that homogeneous solution, which we'll call x sub h, y sub h? It's negative, no it's not, it's b over d times some integer t, or any integer t, and the y coordinate is negative a over d times that same integer t. B, let's see, that's 75 over 15. And A is 180 over 15. And what is that, 5? 5t, and holy moly, was that 12? Negative 12t? Well, let's say 5 times 180 is 900. And 12 times 75, let's see, 750 plus 1. Yep, okay. that's what it is. So this is the homogeneous solution, 5t, negative 12t, where t is any integer. The grand finale, what do we do next? We take our particular solution and add the homogeneous solution to it, right? Step 4, the general solution is the sum of the particular solution and the homogeneous solution. I hope I've recorded these right. I erased the board and then forgot what the particular and homogeneous solutions were. So I sort of did a quick study to figure these out. I hope I remembered them correctly. Anyway, this is what I remember the particular solution to be. I hope it is. And this is our homogeneous solution. And t can be any integer. If we combine these two ordered pairs, this is our general solution. Now, in the question, I think they asked if there were more adults than there were children, how many attended? We want to answer that. I think this is the essence of the question that we had to answer. If more adults than children attended, how many of each attended? X is the number of adults, Y is the number of children. So what we have is X is greater than Y, and Y has to be greater than 0. But we can't have a negative number of children attending. So let's hone in on this. Y greater than or equal to 0. And this is our Y. This is our X. So this means that Y, 3,000 minus 12t, is greater than or equal to 0. So we'll solve that first. Greater than or equal to 12t. Oh my goodness, what's 3,000 divided by 12? Let's see. Divide both sides by 3. 1,000 is greater than 4. So 250 is greater than t. Okay. So from this part of the inequality, we got that 250 is greater than or equal to t. Now, x greater than y, here's our x, negative 1,200 plus 5t is greater than y, 3,000 minus 12t. And let me make sure I wrote that correctly. Negative 1,200 plus 5t greater than 3,000 minus 12t. Okay. Hopefully I wrote that correctly because because it's lost and gone forever now. I'll add 1200 to both sides. And I'll add 12t to both sides. Holy moly. I don't have a calculator. Let me just take a quick break to figure out what this is. Okay, my long division tells me that t is greater than, see, what did I have? 247. It was approximately 247.5. Both of those inequalities have to be satisfied. T is less than or equal to 250, so T could equal 250. Now let's see. T could be 249 and 248 because those are greater than 247. Could T be equal to 247? If T were equal to 247, would it be greater than 247.5? Okay. So values of T equal 250, 249, and 248 give us viable solutions. Let's see what that works out to be. Okay, we plug each of the values of T into our solution. For T equal 250, we plug that in for T. And 3,000 minus 12 times 250 is 0. This is going to give us 50 adults and 0 children. And let's see. I'm thinking this is going to be 45 adults. Let's see, what's the difference between this and this? 5 times 250 minus 249 is 5 times 1. Yeah. So let's see. We have 45 adults. And we have 12 more children. Okay. For T equal 248, we have one less adult here than we do here. So that's 40. And we have 12 more children here than we did here. So that's 24. Now let's see. Why couldn't we go any further than this? Well, let's see. If we did, we'd have 5 less adults, 35. We'd have 12 more children, 36. had T equal 247. We have 35 adults and 36 children. But the original problem stipulated that we would have more adults than children.